Okay, today we're looking at 15.2, which is the action potential, and I'm going to start off with some big ideas around it, and then I'm going to take you through each step and how it happens and what happens. As I said, we're going to be talking about some big ideas. So let's start by the idea that you were told in year 7, that it is electricity that travels down neurons. Now, actually, what we mean by that is electricity as a difference in potential charge. In other words, if you've got a cell that is at minus 70 millivolts and you've got ions that move in, we've got charge on the move, that is electricity. We're also going to think about the axon as that long, thin strand of cytoplasm that's surrounded by a cell membrane. But in actual fact, we're going to imagine that we've cut down it and we're looking this way. So when we talk about it for now, let's just consider our cell like this. And as we've mentioned, there is a potential in charge. Cells are resting. They have a resting potential when the inside of their cell is relatively negative to the outside. That's not to say that that is the charge, it is the relative charge between the inside and the outside of that neuron cell. Let's just think for a moment how we might have established that minus 70 relative charge between the inside of the neuron and the outside of the neuron. Well, you might think we did it using negative ions, but we didn't. We did it using just sodium ions and potassium ions, remembering they both have a positive charge. Because what we have is pumps around the neuron membrane. Remember, this is a phospholipid bilayer. So these ions, because they're water soluble, can't just move in and they can't just move out. They need some special way of moving. And what we've got is these sodium, potassium pumps, and how they work, they use energy, and for every 3 sodium ions that they expel, they allow 2 potassium ions in. Well, straight away, what that does is it creates a difference in concentration gradient. Because if I think about on the inside here, I've now got a high concentration of potassium on the inside, and I've got a high concentration of sodium on the outside, just due to this sodium-potassium pump. So let's just leave that alone for a moment and we'll come back to it in a second. I've already said we've got sodium-potassium pumps. Additional to this, we've got protein channels throughout the membrane. And some of them, which are potassium channels, are just open all the time. But most of them are under the control of voltage. They're under the control of the relative difference between the inside of the cell and the outside. They are called voltage gated channels. And of them, we have got some sodium ones, which are always closed. So here's my sodium and they're closed. Here's my sodium and it's closed. We've also got some potassium ones that are also closed around the cell membrane. So let me just recap. It's a busy membrane. Phospholipid bilayer doesn't let ions pass through it because they are water soluble. We've got sodium potassium pumps, which are swapping 3 sodiums out for every 2 potassiums in. That creates the negative charge. We've got some potassium ion channels that are permanently open. We've got other potassium channels that are closed, and we've got sodium ion channels that are also closed. But we've said they will open when the polarity of the cell starts to change. We've said at this state, this is resting potential. The cell is at rest, it hasn't been stimulated. Now let's think of this really easy example. Imagine we're talking about a pacinian corpuscle. That is the receptor that is in your skin. Imagine I'm going to push part of your skin, but I'm not going to push it very much. In fact, I'm going to touch part of your skin. You can't even feel me touching it. What I'm doing is I am distorting this sodium ion channel. I'm distorting it so that, let me just draw that one back through. I am distorting it so that the whole thing changes shape and the channel opens because I've pressed on it. Okay? So, what we're looking at there is, as I've pressed on there, and I want to remove this bit here, and I want to remove that bit to show you that if I press on that, it's distorted the membrane and the channel is opened. Well, let's just think about it. This sodium has been on the outside, it's been pushed out. So now I've got a high concentration of sodium, and what's going to happen is sodium is going to rush in along certainly a chemical gradient, because you've got high concentration of sodium on the outside compared to the inside. We've also got an electrical gradient. Sodium is running in along an electro-chemical gradient because it is positively charged and it wants to move in towards the negative to balance out that charge. Remember, that's what we said electricity actually is. So let's just think about it on a graph for a second. We've got 0, I'm just plucking these numbers out of thin air. We've got plus 40 and we've got minus 70. We've got resting potential, and then we get a disturbance in that because we get some sodium ions moving in. Now, if it's not a very big touch, if it's not a very big distortion of the membrane, then what's going to happen is the sodium potassium pump is going to kick in enough that it's going to sort it out and bring it back down again to its resting potential. However, if enough sodium ions come running in that it gets to threshold, then what's going to happen is that if enough sodium ions come in other words, if the generator potential is big enough, what happens is those sodium ions run to the other sodium ion channels and they tell those to open. So if the distortion of the membrane is big enough, then instead of the sodium potassium pump sorting it out there, what's going to happen is the sodium ions are going to rush in. They're going to tell the other sodium channels to open, and the polarity of the cell is going to change. It's going to reverse. Let's just look at that again. We've got sodium, potassium pumps. They're just working away all the time. They've created a chemical gradient. We've got sodium channels that are closed. We've distorted the membrane as we've pressed it, and that has opened the sodium channel. The sodium has rushed in, and in doing so, it's reversed the polarity of this membrane potential. It's rushed in along an electrochemical gradient. Now, when it reaches plus 40, what happens is several things. Number one, these channels snap closed again. So this disappears. The other thing that happens now is the potassium channels that are part of this system. We've got the ones that were open all the time anyway, but we've got some that were closed. When the voltage gets to plus 40, that's the signal for these voltage-gated potassium ion channels to open. So I've just refreshed that diagram for us a little bit there. What we've said is you've pressed on the sodium channels, the channels have become distorted, the sodium's run in along an electrochemical gradient. Why? Because it's a high chemical gradient, because you've got a lot of sodium on the outside. It's an electrical gradient because it's minus 70 on the inside, so it's running towards its charge. At the top, when we've got plus 40, the closed potassium channels then open. And let's think about what that does. Remember, the sodium-potassium pump was pumping 2 potassium ions in all the time. So we've actually got a high concentration of potassium ions. So the minute those channels open, what's going to happen is potassium is going to start flying out. Not along an electrical gradient, because at this point, the electrical gradient is it's relatively positively charged on the inside compared to outside. But it's going to fly out along its chemical gradient. As it flies out, it's taking some of the positives out, so it's going to work to reduce the charge, the positivity inside that cell. So going back to here, the potassium ion channels are opened, the potassium is flying out of the cell, and then eventually the sodium-potassium pumps take over. They hyperpolarize a little bit, they get it wrong a little bit, but that is important later on. We do come back to that and explain that. And then it continues to level off and the whole thing is restored. There's a relatively negative charge on the inside compared to the outside, our resting potential. The next thing we need to think about is our generator potential. Our generator potential is the distortion of the membrane in this example, where the sodium ions come in. Is the generator potential big enough to reach threshold? In other words, is there enough sodium ions coming in to tell those other sodium ion channels to open? If it is big enough, we reach threshold. When threshold happens, all the sodium ion channels open and the sodium comes flying in. It's along a chemical gradient and it's along a electrical gradient. And that is when we get an action potential, which is the reversal of charge in the cell. Here, it's repolarizing. So we get repolarization. And at the bottom, we get this hyperpolarization. Hyperpolarization. I'm just going to take you through a flowchart of the whole event from beginning to end. This is the generation of a nerve impulse, and we come back to it in our following lesson. Okay, so just reminding ourselves, what is an action potential? Well, it's something that's caused by a stimulus. It changes the shape of channels in the membrane, namely sodium ion channels. and it causes a reversal of charge. Moving to the next slide. How does an action potential occur? We have a change in shape of the membrane. In our example, it was a pacinian corpuscle, and the distortion changed the shape of the membrane, causes the sodium channels to open, causes sodium to move in along an electro-chemical gradient, causes a generator potential. Is the generator potential big enough? If the generator potential is enough and enough sodium ions move in, we reach threshold. The consequence of threshold being that it opens more sodium ion channels, and then they all come rushing in. The cell becomes depolarized, and then at plus 40, those sodium ion channels snap shut, and of course the next thing is going to be to repolarize it, that we have the potassium channels open. These channels are voltage gated, and because it's the millivolts that causes them to change shape, which is what makes them open or close. Potassium ions rush in along a chemical gradient, causes an overshoot in the electrical gradient. We saw that with the hyperpolarization, and that's what causes the potassium ions to close. The cell's completely repolarized, and that's the end of the story. Okay, so where do students go wrong with this topic? Well, in describing what we've talked about so far, we need to remember that in biology we have to talk about where things move from and where things move to. You need to talk about the channels changing shape. Remember, it's the difference in charge that makes the proteins change shape, which makes the channel open or makes the channel close. That is then what allows a particular ion to move in or out. You need to make sure that you've got your vocab sorted. Can you describe resting potential, threshold, generator potential, hyperpolarization?